start the recording. So, hello everyone. Thanks for joining in. Today we have Professor Matthew Colless with us to give us the history and mystery talk on the Hubble's constant. So this is a series which we ASACR chapter started to cover aspects of science which are not covered in conventional scientific talks, to include as the title says, the history and mystery of a particular topic. And it's my absolute pleasure to introduce Professor Matthew Colless from ANU to give this talk. Professor Matthew Colless is a distinguished professor at RSANU. He was also the director from 2013 to 2022. He completed his Bachelor's of Science from Sydney and then moved for his PhD to Cambridge. Following research fellowship at Durham, Pitt National Observatory and Cambridge, then moved as the director of the Australian Astronomical Observatory, AO, from 2004 to 2012. His research focuses on understanding the formation and evolution of galaxies, mainly through large spectroscopic survey, mapping large-scale structures and motions, and measuring cosmological parameters, a part which he will discuss with us today. He has received numerous awards and honors. To name a few, he's a fellow of Australian Academy of Science, the Australian Astronomical Society, and an honorary fellow of the Royal Astronomical Society. He has been also awarded numerous awards. To name a few, M.K. Venubapu Gold Medal by the Astronomical Society of India, ISI Citation Laureate, and ISI's Highly Cited Researcher Award. The Peter McGraw Prize, the Officer of the Order of Australia, and most recently the Robert Ellery Lectureship by the Astronomical Society of Australia. With this, I would ask Matthew to take it over. Thank you.
Well, thank you very much, Amit. Thank you for that introduction, and welcome everyone. It's great to be able to talk to the ECR chapter colloquium series on history and mystery. The Hubble constant is a great topic for this because it's got a very long history stretching back over 100 years, and it also presents a mystery. We have at the moment something that's called the Hubble constant tension, and that is indeed a big mystery. It's probably the most prominent mystery in all of cosmology at this time. So it's a great topic for this series, and I hope I can do it justice. There's a lot of material to pack into under 45 minutes, which Amit assures me is my limit, so I will try and do that. Here's what I'm going to talk about. Let me give you a quick outline. I'm going to quickly remind you what the Hubble constant is and why it's important. Then I'm going to give you a slightly longer history of the Hubble constant and point out that it's not one controversy, but in fact a long series of controversies right from its very inception. Then I'll talk mostly about the current state of play, where we're at with measurements of the Hubble constant, how it's being done, how the different measurements are in tension, and whether or not it's a crisis. And then I'll briefly discuss potential solutions to the tension, and it'll be brief largely because the solutions are so very unsatisfactory at the moment. So I'll give you a bird's eye view of the various observation and theoretical possibilities that might help us resolve that. And I'll finish up with future prospects, how we might go about resolving the crisis. And then for those of you who are interested, I'll provide a handful of key references and further reading. But let's start right back at the beginning of modern cosmology. For me, at least, modern cosmology starts with Albert Einstein, Alexander Friedman, Georges Lemaitre, and Edwin Hubble, who showed that the observable properties of the universe could be explained in a single coherent physical framework, an expanding universe governed by Einstein's general relativity. And all of that grew into what we now think of as modern cosmology. So on the right there, you can see Einstein peering through the Mount Wilson reflector with Edwin Hubble with his trademark pipe in his mouth. And on the left, you can see on the far left, Alexander Friedman, whose Friedman equations form the basis of modern cosmology, and Georges Lemaitre, who was the father of the expanding universe, who showed that indeed the most likely solutions to Einstein's field equations involved an expanding universe. And those field equations are shown in the top left picture, which is a abandoned railway somewhere in the Atacama Desert. And the person driving the engine there is Bruno Liebengut, who's had quite a bit to do with using supernovae to measure the Hubble constant. So these are our early characters in the play. Lemaitre takes center stage early on, however, because he was the first person to derive and estimate the expansion rate. Here's a clip from a paper of his showing how he derives something that is recognizably, even if in French and slightly different notation, what we now call the Hubble-Lemaitre law, which in its modern form simply says that c times the redshift, the speed of light times the redshift is equal to the Hubble constant times the distance. That recession velocity, cz, are proportional to distance, and the constant of proportionality is what we now call the Hubble constant, even though it's the Hubble-Lemaitre law. More than specifying the law, he also gave the first estimate of that law. And in fact, one of the things that intrigues me is that right from the very start, he was using the units that we use today, kilometers per second per megaparsec. The only odd thing about it is he gets the number which is somewhat larger than the numbers we get today, 575 kilometers per second per megaparsec, which would have given us an age of the universe under 2 billion years, which even at that time was probably beginning to be a problem. Hubble, of course, after whom the law was originally named until it was renamed officially by the International Astronomical Union only this century, in fact, was the person who popularized the idea of the expanding universe by actually making enough measurements to show that there was indeed a proportionality between velocity, recession velocity on the y-axis of this plot, and distance on the x-axis. Although he too got a measurement which was wildly larger than required because they were grossly underestimating the distances to things at the time. So in the early days, a number like 500 kilometers per second per megaparsec was popular. Now, of course, all this stems from Friedman's solution to the Einstein field equations, as subsequently modified by others. And basically, this says that cosmology 101, a homogeneous isotropic universe, has a Friedmann-Lemaitre-Robertson-Walker metric, which means that it results in an expansion history, by which I simply mean it has an equation for the rate of expansion as a function of redshift, which is given by one of the Friedmann equations. Here in modern form, h of z, the expansion rate at redshift z, is given by the expansion rate at redshift 0, h naught, times a bunch of factors that have powers of 1 plus z with constants in front of them. And those constants in front of them depend on the density, energy density in matter, radiation, dark energy, and curvature, which are the critical energy constituents of the universe, as measured in units of the critical density at redshift 0. So we've got a nice simple form for the expansion rate of the universe in terms of the physical constituents of the universe, and the whole thing is given an absolute scale by the Hubble constant. So here we have CZ versus distance for various different cosmological models. And of course, for most of those models, that's a curved relation. But down at small distances, they all come together in a simple, approximately linear equation, which is the Hubble-Lemaitre law. And the point is that the Hubble constant is the most critical overall parameter for the universe because it sets the age scale of the universe in units of the Hubble time, 1 on h naught, and the size scale of the universe in terms of the Hubble scale, c on h naught. And of course, as I said, the expansion history, if you follow it further out, gives you the amount of each physical constituent and also the equation of state of dark energy. But we're going to be concerned only with that first gigaparsec or so, where we're looking at an approximately linear relationship. And we're going to be trying to use that to set the scale of the universe, the age and the overall size of the universe. The physical contents of the universe are encoded in its expansion history on large scales. So how can we go about measuring H naught? Well, we've seen how it was very quickly done in the early days by Lemaitre and Hubble. They had what they believed were estimates of the distance, which turned out to be very wrong. But they were basically finding ways to measure distance independent of redshift so that they could plot the recession velocity, CZ, against the estimated distances. And that's basically what we still do. And in fact, their version of it, which is the distance ladder version, is still the most popular version today and is still a critical element of what we do today. Basically, you use some distance estimator, and we'll talk more about those in much more detail later. And we compare it with overlapping distance domains. So some distance estimators work very precisely, but they tend to be the ones that only reach small distances. So we have a calibration chain linking more precise nearby distance indicators with less precise, more distant indicators. Then we have physical methods where you determine either a luminosity or length directly through some physical measurement or model. And this encompasses geometric methods like megamasers and baryon acoustic oscillations. It includes the strong gravitational lensing time delays, supernova physics models like the expanding photosphere method or modeling of thermonuclear supernovae, the Sunyaev-Zeldovich effect in galaxy clusters, and most recently, gravitational sirens, how we use measurements of the gravitational waves from merging black holes to get a distance estimate. And then finally, the third class are global solutions, where you simply take some measurement of cosmological parameters, which allows you to actually fit a whole cosmological model, including H naught. And classic examples of this include fitting the cosmic microwave background and redshift surveys, where you're using either the CMB power spectrum or the galaxy power spectrum as the thing you fit a global cosmological model to in order to get your H naught. So the evolution of the Hubble constant estimates has had what I would consider to be three major epochs of its own. The first was this epoch, when we went from the early Hubble Lemaitre estimates and got much more sensible estimates of distances so that we got into the right ballpark. So this is what I will call the times 10 epoch, where the epoch is labeled by the uncertainty in the Hubble constant. And we went from having it wrong by a factor of 10 to having it at least in the right order of magnitude. Then from the 70s through the 90s, we had another epoch, the times 2 epoch, where in fact the Hubble constant had two distinct values. The school of Sandage and Taman and collaborators tended to get values around 50, where the school of de Vaucouleurs got values closer to 100. And then finally, we have the modern epoch, which is the expanded box there shown on the right, where again, we have a bimodal distribution, although with a lot more scatter, as you can see. So now we have two formally distinct methods, cosmological measurements of the Hubble constant, which give a low value around 67, and distance ladder studies, which give you answers around the mid-70s. So this is the 10% era. We've measured the Hubble constant with of order 10% precision, but individual methods have bigger scatter than that, or when you combine them, they give you small scatter, but depending on whether you start at high redshift or low redshift, you end up either with a low value or a high value of the Hubble constant. So let's see how we get to this. Here's the classical distance indicator. Here's Sandage and Taman, the days of hand-drawn diagrams back in the good old days of the 1970s. But they had a Hubble distance ladder which worked very similarly to the way that it works today. You have the domain of the Cepheids, the nearby measurements where you can measure things accurately. Then you use less reliable things. They were using H2 regions and brighter stars. And you're trying to reach out to the pure Hubble flow. You need to get out to distances like 5,000 kilometers per second, because at smaller distances, the Hubble flow is smaller than the peculiar velocities of the galaxies or clusters or objects that you're actually measuring. Those peculiar velocities are due to the inhomogeneities on small scales of the universe. You need to get to large enough scales that the overall expansion of the universe dominates those peculiar velocities. And that doesn't happen until you're out at a few thousand kilometers per second. And of course, as I was saying, Sandage and Taman were getting values of 50 kilometers per second, whereas with essentially the same data and methods, Gerard de Vercellez and followers were getting values around 95 kilometers per second. This was another Hubble constant tension. We have the modern one today, but this was a tension in what were then the good old days. Today, we would simply say with limited data, your answer depends on your priors. And these two groups had very strong priors and did some very dodgy data analysis at times in order to make sure that they tended to get answers which are accorded with their priors rather than with what the data were telling them. However, they did set up, despite that significant flaw, what is essentially the set of distance measures that we use today. And I'm not going to list them all, and I'm not going to get into the details and pros and cons of each one, because I want to stay with the cosmological consequences. But nonetheless, by the 1990s, we had a set of distance estimators which were very, very similar in terms of the distance ladder to the ones that we have available today. And so we end up with the classics distance ladder at the time of the Hubble Space Telescope, where we have the reliable local indicators reaching out into the Hubble flow with things like the Tully-Fisher, the fundamental plane, and supernova, mostly supernova type 1a, and things like surface brightness fluctuations. And that was giving us a value of the Hubble constant of about 72. So this was a huge improvement. We'd got rid of that factor of 2. Now we're, for the first time, down in the 10% domain. And this was due to work of people like Jeremy Mould, Wendy Friedman, and Barry Mador, who's not shown in the picture, and also our friend Rob Kennicott, who's shown on the right in that picture. Now, this was a big improvement. You can see that the uncertainty on that thing is around about 10%, plus or minus 7. And we're now well out into the Hubble flow. We're reaching distances of 200 or 300 megaparsec. And we've got some well-calibrated secondary distance indicators. But now in the 21st century, things have got a lot richer. We've got many more things that we can do. We've got the cosmic microwave background, which allows us to directly measure the Hubble constant at very high redshift, but it also gives us a distance scale, the baryon acoustic oscillation scale, which I'll talk more about in a moment, which gives us not just a measurement at the CMB, at recombination, but also a measurement at much lower redshift, because we now have a distance ruler, a standard ruler, as well as standard luminosities from things like supernovae. And then we've got completely new techniques that weren't otherwise available. We've got strong gravitational lensing, which gives us a one-step measurement, doesn't depend on the CMB, doesn't depend on the distance ladder, can get us out to the Hubble flow with a single measurement using time delays for strongly lensed background objects, quasars and galaxies. And of course, we have an array of much more powerful telescopes. We've got the Hubble Space Telescope, we've got James Webb, we've got Planck for the CMB, and we've got Gaia, which is revolutionizing the nearby universe. So we've got a much richer set of tools. And so the modern three-rung distance ladder, which looks very similar in the basics and would be immediately recognized by Sandage and de Vaucouleurs, has geometric anchors nearby, parallaxes, binaries, maser distances to calibrate Cepheid distances that reach out to the nearby galaxies. Those galaxies then allow you to reach out to other galaxies where we've got measurements for supernovae or Tully-Fisher or fundamental plane, and those secondary distance estimators get you out to the Hubble flow and give you a H0 measurement. And if you do that well, as epitomized, for example, by the Shoes collaboration, you get an answer which is now down with an error of around about 1 kilometer per second. So in 2022, Adam Rees and the Shoes collaboration published an H0 based on this sort of distance ladder, which was 73 plus or minus 1 kilometer per second per megaparsec. So we're now getting down well below the 10% error, at least in theory. Our errors are now more like 1 part in 100. We're now pushing the 1% level. So gravitational lenses provide an independent way of doing that. Here we've got some strongly lensed background objects which give us these beautiful, beautiful gravitational lenses. And if you are lucky enough to see the time delays from your background object, then you can get measurements like this. And these typically have errors of around a few kilometers per second. And these are currently giving values around about 73 or 74. So they're quite distinct to, or very similar rather, to the values that you're getting from Shoes and distinct from the values that we're getting from the cosmic microwave background. Now we've got the Planck satellite. Here are the CMB temperature fluctuations measured by Planck. And you can see that there's a stippling on a very distinctive scale. There's these little rice grains of red and blue spots, which are the strongest variations. It's the scale on which the CMB has got its strongest variations. And these are the baryon acoustic oscillations. Those are that first strong peak in the power spectrum, which is set by the scale of the baryon acoustic oscillations, which are frozen sound waves left over from the early universe. In the Big Bang, things were expanding, and then they started to freeze out. And when they froze out, there was a fixed scale for the baryon acoustic oscillations, and that's at roughly 1 degree angular scale. You can see at the top here, 1 degree angular scale that corresponds to the first peak in that power spectrum. The data you can see are the little red dots. They're exquisitely fit by our best fit parametric model, which has got only 6 parameters. And here is that model. We're fitting not just the power spectrum I showed you before, which is the temperature fluctuations. We're also fitting the polarization fluctuations and the cross polarizations between it. But the lambda CDM model with just these 6 parameters provides that exquisite fit to those data points. Quite remarkable. And from those, we get other derived parameters, including which, of course, is the Hubble constant. And the best fit Planck collaboration value for the Hubble constant is 67.4 plus or minus 0.5 kilometers per second per megaparsec. So now we really are down at the sub 1% measurement level. Now, what we're actually measuring there is this, which is the BAO scale. And you can see that that's measured with even better precision than H0, because H0 is a derived parameter, has other uncertainties in it. But the sound horizon scale, the BAO scale, is 147 megaparsecs plus or minus 0.3 megaparsecs. So that's well below the 1% scale. And that's what we use when we want to measure the BAO in the local universe, because that scale is a fixed physical scale that gives us a standard ruler, not only in the CMB, but also in the galaxy distribution, because that imprint of larger fluctuations at a scale of 147 megaparsecs is imprinted on the density field at the CMB at redshift 1100 and is still found in the galaxy density field at much lower redshifts. So down at a redshift of 0.1, for example, that 1 degree scale is now 20 degrees on the sky. And it allows us to probe not only the H0, but also the evolution, the power spectrum of fluctuations gives us the dark energy equation of state, and indeed the behavior of gravity on very large scales. But let's use H0 to measure BAO in the local universe. Here are some measurements from some older surveys, including the 60F survey and Wiggle surveys that I was involved in, but also Sloan and Boss. And when you do that, you find that you get a measurement of H0 of around about 67 plus or minus 3 kilometers per second per megaparsec. So that means that if we calibrate to the drag scale, then we get a local redshift measurement of H0 of 67. This is at a mean redshift, at least from 60F, as low as about 0.1. But all these measurements are below redshift of 1, as opposed to redshift 1100. A more recent version of this from the DESI BAO plus BBN plus the drag scale from the CMB gives us 68.5 plus or minus 0.6. So again, a sub 1% measurement at around about 68 kilometers per second per megaparsec. Okay, so at this point, I want to just point out that there's a distinction here between the redshift at which you're measuring these things and the redshift at which you're calibrating things. So I've got a two-way table here, low redshift and high redshift, measured at high redshift or low redshift, calibrated at high redshift or low redshift. And you'll see that things like BAO and the distance ladder are measured at low redshift, redshift 0 or anything less than 1 for our purposes here. Okay, and so BAO and the distance ladder are measuring H0 in the local universe. They're measuring H0 directly, whereas the CMB, you're measuring H0 at very high redshift, and then you need to apply a model to bring that down to low redshift. So you need to assume a cosmological model. On the other hand, calibrating things in the CMB is easy, not easy. Anyone who's tried to do anything with the CMB knows it's incredibly hard. What I really mean is we seem to be able to do it with very high precision. Everyone gets the same answers. The modeling gives you the same answers, and they're very precise. So in that sense, it's easy. Whereas the distance ladder is hard in the sense that while the observations may individually be easy, it's very hard to get different methods and different observations to give you the same answer. Calibrating it is hard. So you have this payoff, and it looks as if the low redshift BAO are sort of in the sweet spot, that they're both low redshift direct, they don't directly depend on the cosmological model, and they are well calibrated by something. All right, so let's have a look at the H0 estimates by method. On the left, we've got various methods based on the CMB, and you can see that those tend to cluster around low values in between 65 and 70. If you look on the right, you're looking at distance ladder methods, and those cluster around values in the mid 70 to 75 range. Each individual method has got large errors, but you tend to get these clusterings of two methods in the two different regimes. It depends on how you are calibrating your measurements. The measurements themselves are precise. The calibration appears to be the uncertainty. So here, for example, is what the difference is in the H0 measurements between an H0 of 67 and 73 for the Planck CMB power spectrum. Now, if you look at that best fit model with H0 of 67, you get the red dashed curve. Whereas if you use a model with H0 of 73 and the same product of gamma, of omega and H, then you get the blue curve. And they look very, very similar. But in fact, they're wildly distinct in the, they're nearly 10 sigma distinct in the actual fit for the models. Now, likewise, you can also see that there are BAO measurements in the local universe all tend to cluster around the low side, perhaps not quite as low as the CMB itself, which is the grey band there, compared to the shoes band in blue, but in general, all in or around that thing, and certainly all significantly lower than the shoes band. Here's what we hope to be able to do in future with BAO measurements with upcoming surveys like DESI, 4HS, Euclid, or future facilities like MegaMapper or WST. And the crucial point here is that those two grey bands are the same. The precision with the future ones is going to be vastly greater than we can currently achieve, even with the best BOS or EBOS or other measurements. So in future, we're going to have far more accurate BAO measurements in the local universe. All right, let's go back to the distance ladder. The modern version of the distance ladder in the 21st century is in fact a distance network. Instead of having a ladder where things build up from the ground or a chain where every link depends on the other, we're trying to be more robust. We're actually taking the same old methods that we've always used before, sometimes with a bit of a modern polish, but basically the same methods. And we are linking them together in as many ways as possible so that we make it more robust. And I'm not going to go through all the different methods. The point to get here is that a network like this is stronger than a chain. A chain is only as strong as its weakest link, whereas a network, as we know with the internet, can be stronger because it can fall back on other methods if any one link fails us. So here's how it really works. Here's a way of thinking about it, which helps to think about it slightly differently. We start with an absolute distance scale on the left of that middle diagram. You've got your various ways of determining an absolute distance scale. And these are parallaxes and detached eclipsing binaries or masers or modeling of supernovae, whatever they may be. The next step are the anchors. Anchors are where you establish an absolute distance scale based on methods shown to the left. It can be in the Milky Way, it can be in the LMC or SMC, it can be in other suitable nearby galaxies. Then primary distance measures, things listed down the bottom there, transfer that from the anchors to the host. These are galaxies which are sufficiently abundant that they actually provide us with secondary distance estimators. So the hosts calibrate the secondary distance estimators, and they then calibrate the traces. And these are the galaxies or other objects out in the Hubble flow that actually allow us to establish what H0 really is. Now, there are a couple of things which scoot around the intermediate steps. If you do supernova modeling, like the expanding photospheres method, or you've got masers, which you can detect all the way out in the Hubble flow, then you can jump over the middle. But in general, we need to have those intermediate steps. Now, that's the full version of the thing. The baseline version is simpler than that. Here are the different pathways, and I'll let you look at that later. I'm not going to talk about that in detail. Here's the simple version which is being used for the baseline. You use your best absolute distance calibrators, your best anchors, your best hosts, and your most accurate tracers. And if you do that, then you find that you've got these sorts of calibrations. These are the calibrators of the individual methods for individual objects. Those are the data points. And then the overall calibration is shown by the lines running through those points and the bands around them. And these are the baseline local distance network distance modulus residuals for the host galaxies, the calibrators. The groupings share the same method, the same anchor, and the same authors. And so you can see the offsets between different methods and between different authors. And it also shows the individual object errors and the group deviations from the full network value. And if you then apply this, the modern version, you get the modern version of the distance ladder, the Hubble network distance, the Hubble distance network. And these give you the measurements you've got out in your Hubble flow. You've got a few megamasers, which give you a one-step method. You've got some more surface brightness fluctuations, and you've got a bunch of type 1a supernovae. The gray bars show you the effect of a typical peculiar velocity of around 250 kilometers per second. And you can see how once you get out into the Hubble flow, that becomes negligible compared to the uncertainties in your methods. And when you do that, as a recent publication, Casatano et al. Show, you get H0 of 73.5 plus or minus 0.8 kilometers per second per megaparsec. Okay, so how does that agree? Well, here are the different methods with the literature. The red highlighted in yellow is the Hubble distance network baseline, and you can see other people's methods, and you can see that really this is just consolidating what's been done by other methods. And you can see again that it's very different to the green band, which is the CMB measurement. And you'll notice that in fact, that's a new measurement that I'll come to next. Here are different baseline. You can vary that method, try different things, and you can see that because the distance network is robust, no matter what you do, including everything, excluding things, picking your favorite thing, no matter what, you get pretty much the same answer and pretty similar errors to the baseline. All right, so what's the modern best estimate of the CMB? Well, if you combine not just the Planck data, but the South Pole Telescope, third generation data, and the sixth data release of the Atacama Cosmology Telescope, so that you've got a much broader range of multipoles that you're covering in the different Planck power spectra, then you get something like this. You get H naught of 67.2 plus or minus 0.35. Now, one thing I want to emphasize here is that we've now got three different groups, all measuring the same thing with the same exquisite precision and all getting very similar answers. If you look in the right-hand set of plots, you can see the measurements from the different groups, Planck on its own, SPT on its own, then the pairwise, and then the group of all three. And you can see that all the estimates for the Hubble constant overlap at 1 sigma, and the best measurement, the overall measurement, gives you the 67.2 plus or minus 0.35. Okay, so this is where we are in the 21st century. What about BAO plus in the local universe? Well, here's the latest measurement from DESI DR2. You can see that here we're trying to do it both with DESI and Big Bang nucleosynthesis, so no dependence on the CMB at all, or by including the sound horizon from the CMB. You get the blue if you just use Big Bang and DESI, and you get the orange if you use the Big Bang and the sound drag horizon. So that compares with the CMB, which is in purple, and which has this big degeneracy along the product of omega and H naught, which is this dotted line you can see there. And you can see that the three agree pretty well at around about 1 sigma, but that they disagree in the right-hand diagram equally profoundly from the Shoes result. And this result is H naught of 68.5 plus or minus 0.6. Okay, so you might ask, how are these things consistent? If we just do a completely, I don't know about anything about astrophysics, but I just want to look at how different methods and things compare. If I toss out individual methods, if I group things together, if I look and assume that either the CMB or the local distance ladder is biased, what sort of answers do I get? Well, you can do this sort of analysis. And the bottom line is that, well, maybe the CMB seems to be a bit less biased than the local distance ladder methods, but that could just be because they're all doing exactly the same thing, whereas the distance ladder methods are, while slightly more disparate, also more diverse and therefore perhaps more reliable. But the bottom line is that we don't just have a tension in 2021, we really do have a crisis. Here are our three preferred methods. Here's the H naught distance network, 73.5. CMB, Planck plus SPT plus ACT, 67.2. BAO plus Big Bang nucleosynthesis, 68.5. And you can see that there is a spread there which is considerably larger than the errors would imply. In fact, this is now a 7 sigma discrepancy, and that turns it from a tension into a crisis. And of course, every crisis is an opportunity. And we hope that this might tell us something interesting about fundamental new physics. So first, let me offer a few comments on this tension. And these are editorial. First thing I'd like to say is that all the individual methods used in the distance network approach are being continually tested and corrected for every conceivable systematic. Everyone is poking them all the time. There are papers every single day on arXiv proposing a new potential systematic, and then a week later there will be someone having tested that, either corrected it, proving that it was small, or showing that it doesn't apply at all. There's very few ideas that have not yet been thought of for screwing up these things that haven't been measured, tested, corrected, or shown to be negligible. We're really running out of ideas there for ways to go wrong there. Secondly, again, I'll just emphasize that the distant network results don't really depend on any one method or calibration. If there's something you can prove is completely wrong, it won't really change the results, as I've already shown you. Next, a similar thing is true for the CMB. We now have 3 different sets of measurements, all of which give consistent results, some on the ground, some in space, reduced by different groups of people. Again, testing every conceivable thing that could go wrong with those measurements, all the foregrounds, all the analysis, all the physical assumptions, and they are exquisitely in agreement and give very similar results for H0. Now, even though the CMB results in the final form I've given you assume a flat lambda CDM universe, in fact, they don't change much for any standard variant of the model that's also consistent with the observations. Unless you want to fundamentally change the basic assumptions of cosmology, it's very hard. You're so over-constrained by the CMB, by the BAO, by everything else that we now know about the universe, that it's really hard to get a different answer for H0 while not screwing up other observations that we already have. And finally, the BAO plus Big Bang nuclear synthesis H0 is calibrated by physical results from the CMB era or earlier from the BBN, but is measured at low redshifts. So it doesn't really depend on the cosmological model, right? You need to either misunderstand Big Bang nucleosynthesis, which is pretty well tested, or you need to misunderstand the physics of the era of recombination, which give you that physical scale for the BAO scale. But those are physical measurements. They just transfer themselves down to today. You don't need to actually have a model for the cosmology to get that. And they still agree with the CMB. So overall, the wiggle room in the H0 measurements is now quite limited. Okay, so what are those solutions? So there are some basic general classes of solution. There's a million things out there. Carl Glazebrook has this wonderful word cloud, which I didn't actually include, but which in teeny tiny font just lists the name of every possible solution to the H0 tension, and it fills the whole screen like this in teeny tiny top font. I wanted to give you something slightly more intelligent, which is to give you the general classes of solution. So one class is a local void. But in order for that to work, you need an underdensity in terms of the contrast relative to the mean density of the universe of minus 0.8, where minus 1 is a completely empty void. So minus 0.8 is a pretty damn empty void. It's not a small underdensity. Furthermore, it needs to be big. It needs to reach out to something like 12 or 15,000 kilometers per second. So this is a volume whose diameter is about 0.1 c, right? That's a big volume. And this turns out to be a 20 sigma fluctuation in lambda CDM, or indeed in just about any universe which has fluctuations consistent with the CMB and with the local galaxy fluctuations. Not really a good model. Simple, no new physics, but it doesn't really work. Then there are early modifications of the expansion history. This is basically saying, I just want to change everything from the very beginning. I want to screw up the CMB measurements and the local distance measurements and change everything. Then you could say, no, I'm going to stick with the CMB. I'm going to have a late modification of the expansion history. So the CMB is all fine. All the problem is with the actual local expansion rate. It's not what you think it is because things have changed. Then there are ways of changing recombination. This is tempting because if you can change recombination, you change the CMB and you change the BAO scale. So you can change both of those at once and not need to change the local universe at all. and this is favored by people who like the distance ladder. Their mantra is the thermal history of the universe does not have to be the same as the ionization history. So the thermal history is what you have for the expansion, but the CMB is actually changed by some ionizing events early in the history that we haven't accounted for, primordial black holes or something else. And so it's not what you think it is. Another option is to change inflation. Hey, we have two epochs of inflation already, right? We've got inflation just after the Big Bang. We've got effective inflation today with the accelerating universe. What's a third inflation between friends? Let's add another round of inflation and fix things that way. And then you've got modifications to the theory of gravity, which you might like to invoke to get rid of dark matter and other things as well. So they're tempting. The problem is that none of these is really satisfactory, as each exhibits one or more of the following flaws. Many of them only partially resolve the H0 tension. In other words, no matter what you do, you don't actually fully bring the two sets of measurements together. Or worse, at the same time, you make other sorts of tensions like S8, which I haven't got time to talk about, which is to do with the scale of fluctuations. You make those actually worse. And those are actually a more general subset of the fact that none of these really fit the full array of cosmological observations any better than, or indeed in many cases, even as well as lambda CDM. It's a really good model. It's hard to do better in every respect while fixing H0. Another unsatisfactory aspect of them is that many of them invoke additional unexplained physical entities. Now, we already have, dark energy, we have dark matter, we've got inflation, we've got the weird entropic state of the universe at its outset. We're already calling on a small herd of unicorns in order to have lambda CDM. So adding unicorns to the herd may be tempting, but isn't really going to be very helpful. So finally, some of them, like the local void, actually revoke the cosmological or Copernican principles. And that's even less tempting than another unicorn in the herd. All right, I'm nearly done, Amit. Sorry, I've gone a little over, but I'm very nearly there. So let's think about then how people are responding to the H0 tension in 2025. One is people sticking their heads in the sand. This is a very popular technique at all times, in all ways, and humans being humans say nothing to see here. Residual biases in multiple distance ladder methods, plus underestimated errors, or the same thing for the CMB, mean the significance of the whole thing is overestimated. Well, it is still just possible, but I hope I've convinced you that this is, I would say, extremely unlikely, or at least one would have to say increasingly unlikely. The second response is, okay, well, there's something going on here, but maybe some non-fundamental change in the cosmological model, such as earlier reionization or tweaking with recombination, will bring CMB results in line with the distance ladder. We only need to reform the cosmological model, not change it completely. Well, as I've said, this is hard to do and is increasingly unlikely, just like the other method, because there are so few ways you can change the model without radically changing it that actually allow you to account for the difference in H0. So that leaves us with revolution. A fundamental change to the cosmological model is required. This means new physical constituents, say early dark energy or something, a major reinterpretation of GR. Back reactions from inhomogeneities are much more significant than we currently think, or in fact, modifying non-GR, a new theory of gravity. So these things are also hard to do for exactly the same reasons, but give you many more levers to play with, so allow you to fit both the Hubble tension and still fit the whole cosmological model. It's hard to do, but it seems increasingly likely. There's no answers at this point, but if you are a betting person, then the odds are beginning to shift in the direction of revolution. So finally, future prospects. For BAO, DESI and Foremost are going to measure the BAO scale with millions of galaxies, tens of millions of galaxies over the whole sky, out to redshift 1. They'll give the BAO scale to 0.1% precision and give a well sub 1% low ZH naught estimate, and also a sound horizon-free estimate with 1% precision purely from the shape of the galaxies without using any information from the CMB or the Big Bang nucleosynthesis. Supernovae type 1a and lensing will be revolutionized by LSST and Rubin. It's going to detect 250,000 supernovae type 1a per year. And at the end of the survey, there should be a few hundred that should yield H0 from strong lensing time delays, and a few 100,000 that might yield H0 from light curve distances. Again, you need to solve that low Z calibration, but you're going to have a spectacular sample of type 1a supernovae and strong lensing. Then we might also be able to use type 2 supernovae. Again, LSST is going to have all these millions of supernovae. If we can refine the expanding photosphere method or some other method, then we can get a high precision H0 estimate from self-calibrated one-step distance indicator using the very abundant type 2 supernovae. A new entry is gravitational wave sirens. If we could get a few hundred bright sirens, i.e. localized known host sirens, or a few 100,000 dark sirens where we just have the gravitational waves, then that would yield a self-calibrated one-step H0, again with 1% precision. And finally, there's always the option of a theoretical breakthrough. Being an observer, I am skeptical, but you never know. We will have to wait and see. So that's the state of play in 2025. If you want to read more about it, there are 3 excellent references I can refer you to. There's the Hubble Constant Tension book, which is a whole series of edited essays by experts in all the things that I've talked about, going into vastly more depth than I can. The Hubble Distance Network is reported in this paper by Casatano et al., which gives you a really good overview of where distance ladder, distance network things are right now. And then if you want to look at the Hubble tension in the context of all the other problems cosmology has, then I recommend Challenging the Standard Cosmological Model, edited by Binny Mahayi and Peacock and Sarkar, which came out this year from a conference last year. Great series of books that I can strongly recommend for further reading. And that's it. Thank you. Sorry for running over time.
No, thanks a lot, Matthew. That was a fantastic talk. We now have time for questions. I think we just got a comment on your interpretation slide from Darren saying, my reaction is I have enough other things to worry about. But yeah, this was great. People, it's time for questions now. If you have any questions, please go ahead. Lots of virtual hands. So while people are thinking, I would take this opportunity, Matthew, to ask a question. And usually we ask about this, like what is the most and least favorite aspect of this history of Hubble constant for you, like personally?
Okay, so in fact, I'm going to sort of cheat. I might answer it more than once, actually. So one thing that I love about the modern version of all of this is just how collaborative and interactive it is. The fact that we have these large groups of people from multiple different surveys, different methods, all working together, working really fast in a very modern, networked way in all senses of that term, making suggestions, making corrections, improving things, and doing so with relatively little ego, relatively weak priors on what they do, is a vast improvement of when I entered the scene, which was in the 1980s, when the whole Hubble-Taman versus de Vaucouleurs thing was at its height. And you had to be on one side or the other, and it was, daggers at dawn, duel to the death, and, no quarter asked. And it was very not this. And so that was how the scientific method goes wrong. People become too attached to their theories, their personal preferences. And I think that was exactly how it shouldn't be done. Whereas I think today we're doing it in a much more healthy landscape and in a much stronger way. Both, we've got much better data and information, obviously. We understand the universe much better, but I think the sociology is also vastly better than it was in the old days. So good old days, not so good.
Thanks, Matthew. And another question was like this, from your talk also, it seemed like this is a very rich field in terms of data, like more data is coming up and uh, uh, so is there space for like all of this machine learning in AI, or have people started already using it in this particular field, or do you see it being a valuable tool going ahead?
So it's being used in a number of ways already. So, for example, people are using machine learning emulation to speed up the calculations of all the vast Monte Carlo. I'm going to combine all these vastly complicated different data sets together in order to get the best answer. I'm actually using machine learning to try and improve some of the methods. So, for example, I'm an advocate of using the fundamental plane. And the fundamental plane's big problem is that it is not a very accurate distance estimator. You can only get distances of order 25%. And that means that it's at a increasing disadvantage against all these people like Brian and co, who are using supernovae and who have 8% distances. And at the moment I can say, yes, but I've got tens of thousands of you only got, a few hundred or a few thousand. Well, in future, I will have hundreds of thousands of fundamental plane things, but they might have 100,000 supernovae, and so they win. So I need to get my distance measurements down. So I'm using machine learning to see if by including other measurements, including other information, we can use an enhanced version of that to get it smaller. And in fact, I've got a undergraduate student here at ANU who's showing that indeed we can probably reduce the scatter around the fundamental plane by perhaps as much as a factor of 2. And so actually keep it competitive with the supernovae for much longer. So yes, machine learning is being used in various ways, and I'm sure will be used in many more before we're done.
Thanks, Matthew. The next question is by Ron. Ron, please take it over.
Um, oh, hi, Matthew. I hate to see question time not being used, so I just wanted to reinforce what you said about the bad science in the 70s and 80s. So my active period was primarily also in the 70s in particular. But I was just going to slightly question. So in that period of the 70s, Sandage versus de Vaucouleurs, the groups were antagonistic. But I did notice that this huge bias of people wanting to get the answer which they thought was the right answer was really what was biasing both of those groups very much, which is what you said. I'm not so convinced as you are that this has completely disappeared. I see it still as a very common factor that people want to get their preconceived answer, and it takes a big discrepancy before they can be pushed away from it. So, as you said, the Hubble crisis has now pushing people, so they have to move away. But I don't think this bias has gone.
So I think I agree with you, Ron, in the sense of individuals always have that bias. We all have our own bias. My take on this, though, is that we are crowdsourcing the Hubble constant rather than having the hero giant solve the problem for us, right? The trouble with the 70s and 80s was that you had just these small numbers of people with a few hero figures leading them. And so their personal biases mattered. I mean, we still have people with biases today, right? Adam Rees is never going to admit the Hubble constant is not 73, and George Efstathiou is never going to admit it's not 67. But the fact is, they're surrounded now by literally hundreds of people who aren't so measured, who aren't so married to those numbers, and who are willing to solve the damn problem. And so, I think it is healthier, despite the fact that humans don't change much. I think the sociology has improved.
Yeah, okay, I agree with that. I agree with that, Matthew. There was also in the 70s, probably less so now, some individuals like Sandage had complete control of the biggest telescope.
Yes, absolutely.
And he exploited that. That is, other people didn't
Ruthlessly.
get to use the
Yes.
200-inch.
Actually, I can't resist telling my Alan Sandage story at this point. I only ever met Alan Sandage twice. Once when I was a PhD student for the first time in Cambridge, and once much later when I was working on GMT at Carnegie. But the first time I met him was a total unmitigated disaster because I was standing in the library at the Institute of Astronomy in Cambridge, and Alan Sandage walked into the room. And I instantly recognized him, of course. He was my great hero. He was the giant of cosmology at the time. He had his name on more things than you could poke a stick at. And so I went up to him and said, hello. And he said, hello, before I could get my name out, and greeted me like a long lost friend, and immediately launched into this complicated technical discussion about globular clusters and goodness knows what. And I was completely shell-shocked. I had no idea what he was talking about. First, I thought he was completely mad. And then I realized that he, in fact, had mistaken me for some Italian collaborator of his, who obviously, poor soul, must have shared my physiognomy and was telling me all about some work they'd done together, obviously remotely. And I couldn't escape this conversation. And so luckily someone else came into the room that Alan knew, and I snuck away before Alan could discover that I was in fact a lowly graduate student and not his collaborator, and therefore embarrass him. Fortunately, when I met him the second time, he'd completely forgotten about it, so I was able to introduce myself properly instead. Prior.
Yeah. So I have a Sandage story, Amit, unless you have other people waiting.
Please do, Ron.
I was a postdoc at Caltech during the height of this dispute. Alan Sandage, as some people know, was part of the Mount Wilson and Palomar group, and they were physically a few kilometers away from the Caltech campus where I was and most of the astronomers were. And there was a proposal to move the group onto the campus. And Alan Sandage said, only if there are no linking doors between the two buildings.
Yes, that sounds about right. Well, my jaundiced view of that whole thing actually started when I was an undergraduate. I was a summer intern at the Anglo-Australian Observatory and worked with a guy called Dave Haynes, who worked on the H-naught problem and critiqued both Sandage and de Vaucouleurs and all their individual papers, and pointed out all the ways in which they were mishandling the data in order to get the results they got, and put out a review. And was then, if he, today he would have been doxed or trolled or something, but it was the 1980s equivalent of that. And he was very much abused in conferences and in print for having dared to say that either of these groups was wrong. And having sat in the same office with Dave and known how carefully he'd gone through the data and had him explain to me exactly what he'd been doing, I thought that both Sandage and de Vaucouleurs were behaving extremely badly. So I had a strong prior of my own, which was more about behavior than about actual values. Lachlan.
Yep.
Hey, Matthew.
Hey, Lachlan, good to hear from you.
It may have no relevance at all, but I can't help but feel the similarity between in the tension here, in the tension between GR and standard model and the search for quantum gravity. Do you think that's at all possibly an avenue for how this might be solved, or is it just
it would
not
certainly
related?
It would certainly be good to have a fundamental conceptual breakthrough. At the moment, so many of the theoretical models are simply ad hoc phenomenology masquerading as theories. And they have no strong physical motivation, or at least very tenuous motivation. What we really need is the equivalent of general relativity itself, which provided the conceptual breakthrough that gave us modern cosmology. Everything's built on general relativity. And we need that. And so, yes, if there was a genuine conceptual breakthrough in quantum gravity that gave us a revised version of general relativity or explained inflation or whatever, that would be a wonderful improvement. Because at the moment, I think the data is outrunning our theoretical understanding. I mean, the quality of the data is superb, and yet here we are with a model of cosmology which depends on GR, which we can't reconcile with any other of our fundamental theories. It invokes dark matter, dark energy, and inflation, none of which we can properly explain. And so it's a very ad hoc cosmological model, and we need to have a reset of our conceptual base, I think, before we can do much more. The data are going to tighten and tighten the screws on the theory, but whether we get a conceptual breakthrough to match that is open question.
But it sounds like you do think that it's more likely to be a theoretical breakthrough than coming up with some observational, bias or systematic.
I think it's not clear to me that there are in the near future astrophysical observations that can do more than tighten the screws we've already tightened to the point where it's no longer possible to fudge things. But I don't see any observations that are likely to give us a very new bit of information other than, whereas in the past, dark energy was new information, right? I don't necessarily see that occurring in our near future.
One final question, and this goes back to when I was working with you. Whatever happened to kinematic SZ?
Oh, it's still going along. I mean, there's a whole bunch of methods I have skated over simply because they're not the ones that currently tighten the screws on H0. So they're not yet giving precise enough values. So there's a plethora of methods which are useful as independent checks, but they're not at the forefront of precision and aren't likely to be in the near future. And so don't really enter into this particular discussion.
I remember it being the bright shining star that was going to happen.
Yeah, hasn't got there yet.
Thank you. Yeah, so it's very interesting to see how science and doing science has evolved. Thanks, Matthew, for covering it. And maybe a related question to what was already discussed last by Lachlan is this in what seems like a very, very tough observational and data analysis problem. Is there, I mean, is there a place for like a pen paper theory? Something like the first slide you showed, which was like or more of a like a pen paper thing. Is there a place for pen paper thing, or it's all just too complicated and non-linear now?
It's quite possible that someone will come up with a neat new method, right? Things like gravitational strong lensing is a really neat method, right? It's basically a pen and paper method, right? Making the models can get quite complicated, but the basic method is pen and paper. Something like that could pop up. Someone could find something new. I certainly don't rule that out. The hard bit is it needs to be something new that would thoroughly replace one or more links in the chain. It needs to be a completely new way to get a standard candle or a standard ruler or a standard siren or some other standard which we can use. I don't know what that might be, but I certainly don't rule it out. It's amazing how many ways there are to do this, actually. The universe is very richly provided with ways to measure distances. Not all of them are equal, some are better than others. But I wouldn't completely rule out there being other ways of doing it that we haven't yet stumbled across.
Thank you. Yeah, I agree. With this, I will stop the formal recording. So thanks, Matthew, a lot.